studied last lecture? Scanned it? No one?
Yeah.
So, rolling our example of rolling over the sphere. X, Y, and Z. Your sphere. We can use the spherical coordinates, so theta, the exact same thing. And then from theta, you have phi. So this is your mass and this is your radius. The position vector, and you had this from last time, and like I said many times in this course. So the position vector, which is x, y, z, it's r cosine phi cosine theta, cosine phi sine theta, and negative sine phi, right? You differentiate and compute your kinetic energy. You find your kinetic energy 1/2 mr squared cosine squared phi theta dot squared plus phi dot squared. I've seen this several times, and last time we said we can write down the kinetic energy as 1/2 your q dot so q dot transpose mass matrix times q dot. So just for simplicity here, let's assume unity mass and unity r. So your kinetic energy is simply 1/2 the generalized velocities are theta dot phi dot, mass matrix times theta dot phi dot. And from the expression of the kinetic energy, you can fill in the mass matrix, right? So the coefficient theta dot squared cosine squared phi, coefficient of phi dot squared is 1. If we have any theta dot phi dot, we're going to divide it by 2 here and there. Okay, so this is my mass matrix, and it's always symmetric and positive definite matrix. Okay? We know all this from before. Then how we get the equations of motion? Well, the equations of motion are such that the action integral is stationary, so the first variation of the integral of the kinetic energy, if we don't have any potential energy and external forces, so this is the case, is equal to 0, which gives you your Lagrange's equation, right? d by dt partial t partial theta dot minus partial t partial theta 0 gives you d by dt. For this particular example, cosine squared phi theta dot is 0, and the other equation is d by dt partial t partial phi dot minus partial t partial phi is 0, giving you phi double dot plus sine cosine theta dot squared. Now we know that these two equations are simply mass times acceleration, right? Mass matrix, the exact same mass matrix here and there, times your acceleration plus some quadratic terms in velocity representing centripetal and Coriolis accelerations. This is equal to 0 because we are free. Last time we said that this is equivalent to simply a straight line, an equation for a curve with 0 acceleration on our configuration manual, right? So that the motion, the trajectory of the motion is such that it takes a straight line on your configuration manifold, configuration space. In your space, whatever it is, whatever your space is, the motion is such that it moves along a straight line. Okay? Then last time we defined the Riemannian metric. the last thing that we did last time, to define a Riemannian metric, we said it's simply a matrix of function of the states, function of your coordinates, and it's symmetric and positive definite. If you have a matrix that is smooth function of your coordinates, symmetric and positive definite, this matrix tells you a means of doing dot product, inner product. So this matrix, G at a point P, it takes two elements in the tangent space of P, two velocity vectors. One is here, cross, here is the other one, right? And gives you a real number. How the computation is performed? Well, we say G, if V and W are two vectors in the TPM, then here how we perform the computation. We said the dot product between V and W is as if G is acting upon V and W, and this is simply V transpose G matrix W, okay? Which is, if you want to write it in this form, it's summation over I, summation over J, Gij, Vi, Wj. A row times a matrix times a column, okay? You get your real number, which represents the dot product between these two elements. And like we said last time, if you know how to do a dot product, we immediately can define norm. What's the norm of a vector? Okay, it's the dot product of the vector of itself and under square root. And if this is the case, then if I'm given a curve, gamma is a curve, say from 0 to 1 over m. So gamma is a curve on m, on your manifold. Then I can define the length of gamma as the integral over this period, whatever it is, the norm of the velocity vector, right? dt. This is indeed the length of the curve. And if you gonna use this, so this is integration from 0 to 1, the norm of this guy is the square root of G acting on gamma dot and gamma dot, right? So if gamma in coordinates is simply x1 up to xn, then the length of gamma is the integration square root, here is the formula, summation Gij x dot I x dot j dt. I1 to n, j1 to n. Any questions so far? Any questions? Please, if you have a question, just come up with it. Yes, please now.
I have a question regarding the previous part where you have found a straight line. I have a question is like, what if the manifold is curved?
Yeah, I mean this is for a, indeed it was for a curved manifold.
Yes, how can you find a straight line on a curved manifold?
Last time we derived an equation for this, right?
Yeah, but how, I mean, on physically, how is it possible? If you find any 2 points, the straight line between those 2 points can never lie on a curved manifold.
Can never, no. When we say we have a curved manifold, it's as if our world is that manifold. I cannot go outside of that manifold. And we're defining the straight line on that manifold. Okay, it's not, there is no mention of the straight line in the ambient space. There is no ambient space. Our manifold is the whole world. Okay, we cannot see outside.
That is the shortest distance on that manifold.
Either two cases. We did not discuss shortest distance in detail so far, but last time we discussed in detail the idea of zero acceleration. The straight line is a curve with zero acceleration. How can you determine that trajectory? Well, here is the definition of a zero acceleration, gives you second order differential equation, solve it to get the trajectory. Okay? So now we are towards the second definition for a straight line, which is maybe the more well-known, the well-known definition of the straight line, which is the shortest path. But we need to define the length of a path first. So here is a path, a curve, and I need to define the length of the curve. So I'm saying that we cannot define the length of the curve with our previous knowledge. We needed an extra tool. What's this extra tool? Something called Riemannian metric. It's simply a matrix that is symmetric and positive definite, smooth in the coordinates. If you have this matrix, then I can define dot product with respect to this matrix, exactly like in Euclidean space. And if you can define a dot product in any space, you can define a norm. And if I can define a norm, I can measure length. Right? So now I can measure length. Let's look at this here. This is dx by dt, dx by dt, okay? The dt's in the denominator, I'm going to get it outside, and they will cancel this dt. So I'll end up with integration 0, 1, summation, summation, under square root. Summation, summation of what? Gig as is. This guy is dxi by dt, the dt is gone, so this is dxi, dxj. Okay? So this is what? This is the length of the curve. So the length of the curve is simply the integration of ds over the manifold, right? So this gives you an idea of how that line element on the manifold can be written. Simply from this equation, the line element ds squared is the summation gij dxi dxj. So let's get the line element on the sphere. Let's get the line element in the sphere. This is pretty straightforward. So in the sphere we know that xyz is cosine what? Phi cosine theta, cosine phi sine theta, negative sine phi, right? And I need ds squared. So actually, ds squared, these are the coordinates, is simply dx squared plus dy squared plus dz squared, correct? Okay? This is in general in your. I did not specify on the sphere yet. This ds squared for a three-dimensional space is dx squared, dy squared plus dz squared. So if I want to construct a matrix out of that, what do you mean by a matrix? Because my ds squared is simply the coefficients of the matrix, the entries, are the coefficient of dxi, dxj. So the coefficient of dx squared is g11. The coefficient of dy squared is g22. The coefficient of dz squared is g3. The coefficient of dx dy is g12 and so, okay? So you can see what matrix we can construct out of here. What matrix? It's the identity matrix. It's always the case. If you have a flat space, the Riemannian metric on the flat space is simply the identity matrix, okay? It's trivial. On the sphere, no, I'm going to substitute the x, y, and z from the equation of the sphere, okay? So I need to get the dx, square it, dy, square it, dz, square it, and add them together in terms of the coordinates of the sphere. I don't have 3 coordinates in the sphere, I have just 2, and I selected the spherical coordinates, theta and phi. That's fine, so this is something squared plus something squared plus something squared, okay? Any question about that so far? So let's get dx, please. If this is x, here is x, it's a function of phi and theta. So let's just differentiate it. So you get negative sine phi cosine theta d phi, negative cosine phi sine theta d theta. This is dx. Any question about that? Any question about that? You're going to do these things in the homework combined. Okay. Any question about this, dx? Yes, Joseph?
Can you explain more how you get that?
Okay, let's do the y. This is y,
Okay.
correct? So y is a function of phi and theta. So derivative with respect to phi d phi plus derivative with respect to theta d theta. So differentiate this with respect to phi is negative sine phi, and sine theta goes as is. This is d phi. Then differentiate with respect to theta, you get the same cosine phi, and sine theta with respect to theta gives you cosine theta. Okay? And this guy is easy. This is negative cosine phi, right? D phi. Okay? Any question about that? Now I'm going to square things and add them together. Interestingly, a lot will be cancelled, and you will end up with this cosine squared phi d theta squared plus d phi squared. Okay? A lot of terms will cancel with each other. So this is my ds squared, the length element. Immediately define the Riemannian metric G, the matrix. Can you give me your G from here? Again, it's as if I'm writing G as, so as if I'm writing this guy as d theta d phi as a row, G elements, d theta d phi as a vector. Okay? This thing here, Gij, dxi, dxj, indeed is a row matrix form. Okay? Can you give me the entries of the matrix?
Cosine
Cosine
square.
Sine squared
0, 0,
0, 1. Okay, so this is your Riemannian metric. You can now multiply it by velocity vectors to get energy, okay, or whatever. Any question how to get the elements of your Riemannian metric? So if I give you any shape, you're going to do this x, y squared, z squared, and substitute by the relation of that shape. And at the end of the day, you collect the elements to get your Riemannian metric, okay? Any question about that? Okay, so if I have G, like I said, if I have G, I can compute the length of the gun. That's fine.